Hello, last time we have seen cosmic ray propagation, and a problem with cosmic rays is that they are charged particles, so they cannot be used to locate their source because they are deflected by magnetic fields and they arrive at a random direction in the sky. So to locate their source, we need to observe gamma rays and neutrinos produced by their collision near the sources. And so today I want to talk about gamma ray astronomy. And unlike traditional astronomy, gamma rays are very energetic, high energetic photons, and so they must be detected through the methods of particle physics. In astronomy, we use the spectral energy distribution (SED), which plots the energy times the differential the derivative of the flux of particles with respect to energy. So this gives the spectral energy distribution, and usually in the plots the y-axis is multiplied by E, so it is E squared dn on dE, and it is plotted on a logarithmic scale as usual, and we can distinguish between various types of curves. For instance, the spectral energy distribution, these curves, nested curves, you should recognize them. It is from the first video. If you have seen that, it is the black body radiation, the distribution of a black body. They are all nested, and this one, for instance, is the cosmic microwave background. This one very small here, with a peak in the milli-electron volt, which is the microwaves, which is a type of radio wave, and here is also the height I have chosen here is completely random, so just focus on the x-axis, on the position of the peak. The sun is has a peak in the electron volt range, which is the optical range, and the synchrotron. This is the synchrotron curve, which is not a thermal curve, which is not a black body curve. So these are black body curves. Then we have these curves which I have drawn, which are, for instance, they relate to photons emitted by particles in acceleration sites. And for instance, close to a neutron star, there is the synchrotron radiation of electrons, because electrons rotate rapidly and emit synchrotron radiation. And this synchrotron radiation goes from radio waves to X-rays, so it has a peak in the X-rays, so in the kilo electron volt. And electrons not only emit synchrotron radiation, but they also undergo inverse Compton scattering in acceleration sites. And inverse Compton scattering emits much more energetic photons, which are of the order from megaelectron volt to teraelectron volt, with a peak in the gigaelectron volt. They are gamma rays. And so these blue emissions in gamma ray emissions in and X-ray emissions in acceleration sites are called the leptonic model of gamma ray emission. And instead we have also the hadronic model of gamma ray emission. The hadronic model is a little bit different because it does not have two peaks but only one, because synchrotron radiation is negligible for hadrons, and protons can collide with protons in acceleration sites. This creates pions, and the neutral pions, it decays into two gamma rays pretty quickly. And the minimum energy for these gamma rays is half the rest mass of the pion. So these energies are at least 70 mega electron volt. And they also proton can also, as we have seen in the last video, interact with photons, which we have seen photons of the microwave background radiation, but photons in acceleration sites are even more energetic. So we have seen that when they interact with a photon, in the last video, they create a resonance delta plus, which decays into a proton and a pion, and if either or also a neutron and a positive pion. In the case of proton and a pion, the pion can decay into two gamma rays as before. And if you remember, we had calculated the energy threshold for this process for protons in the cosmic microwave background. But here energies are generally, photons here are generally more energetic than the photons in the background microwave background radiation, and so the energy threshold is even smaller because if you remember the formula for the energy threshold, it was proportional to to the inverse of the photon energy. So if the energy is more energetic, the energy threshold is even smaller. Another difference is that between the leptonic and the hadronic model is that we have charged pions in the production of charged pions in the hadronic model, which decay into muons and neutrinos. So we can see neutrinos arriving. So if you see a high component of neutrinos arriving, it means that there are hadrons being accelerated. Now we see some experiments for gamma ray detection. So let's see the CGRO, which is the gamma ray the Compton Gamma Ray Observatory. It was launched by NASA in 1991 and it has operated until 2000 when it was sent to the atmosphere and it burned in the atmosphere. It had 4 experiments on board. One is BATS, Burst and Transient Source Experiment for gamma ray bursts. One is OSSER, Oriented Scintillation Spectrometer Experiment for X-rays and lower energy gamma rays. One is Compton, Imaging Compton Telescope for gamma rays with energies from 1 to 30 megaelectron volts. And one is EGRIT, the Energetic Gamma Ray Experiment Telescope for gamma rays with energies from 20 megaelectron volt to 30 gigaelectron volt. So we will see BATS and EGRIT. And let's start with EGRIT, the Energetic Gamma Ray Experiment Telescope, which could detect gamma rays with energies from 20 megaelectron volts to 30 gigaelectron volts. It did it with a spark chamber. So when these energies, the dominant process is pair production, is gamma annihilating into an electron-positron pair near a nucleus. And so when the gamma ray enters the chamber, it annihilates into an electron-positron pair, which is detected by the chamber, and the direction is reconstructed, and this pair is then absorbed by a calorimeter. So also the energy of the gamma ray is reconstructed. Now you might ask, but what if these electron positrons do not come from a gamma ray annihilation, but they were just electron positrons which enter the chamber? Well, for this reason, there is an anti-coincidence shield with scintillation counters which detect charged particles to ignore, because you do not want to measure charged particles which were already charged particles, once only the charged particles from gamma ray annihilation. So if these counters detect that charged particles have entered the chamber, they tell the chamber to ignore the measurement, because these are not target particles, the target particles of gamma rays. So if a gamma rays passes through the scintillation counter, and so these gamma ray only annihilate inside the chamber, and the charged particles are created directly inside the chamber, and so the measurement is not ignored. Now, the results of these experiments were mapping the sky, the gamma ray sky at these energies, and I did here a wonderful drawing about the map of gamma rays at this energy. There are better pictures from the experiment online, but on the internet, but I think you can recognize the galactic disk. So this means that also through the galactic disk, these processes, these gamma rays, through the galactic disk, gamma rays at this energy are constantly produced. So, for instance, by interaction of a proton with the gamma rays of the cosmic microwave background. So gamma rays are not gamma rays in the cosmic microwave background, but they are in the frame of reference of a very energetic proton. Proton plus gamma rays gives proton plus photon gives some particles like p0. You can get p0 plus or a p plus, and the p0 annihilates into two gamma rays, and so these gamma rays come from annihilation of pi0, then it annihilates itself into an electron-positron pair inside the chamber. Before talking about Batz and gamma ray burst experiments, I want to introduce Fermi Gamma Ray Space Telescope, which is another satellite experiment like the Compton Gamma Ray Observatory. This one was launched in 2008 and it is still operating, so it is like a more recent version of the Compton Gamma Ray Observatory. And it has two experiments on board. One is the LAT, also known as Fermi LAT, Large Area Telescope, which measures, which detects high energy gamma rays, and the other experiment is GBM, the Gamma Ray Burst Monitor, which detects gamma ray bursts. Fermilat is a much more sensitive version of Egret, and this is my wonderful drawing about the map Lat could do with about the gamma ray sky. Well, if you don't see much difference with the previous picture, well, you're right, but this time you can zoom. Lat had much more resolution. You can zoom and maybe also recognize individual acceleration sites like supernova remnants. Another thing I'd like to mention is that with gamma rays we can see the galactic disk. You cannot do this with normal light, with photon. In the sky you do not see the galactic disk because photons are blocked by dust, and instead gamma rays, they pass through dust, and so you can see them. So you can see the center of the galaxy with gamma rays. Identifying individual acceleration sites is not easy with simply a picture because of the diffuse gamma ray background. So protons with colliding with a microwave background, and electrons which collide also with microwave backgrounds. In order to identify the individual sources, you must take into account the diffuse gamma ray background, and this can be done by knowing the properties of a galaxy. Then you can simulate the background from these properties without the source, the acceleration sources, and so you can subtract to this picture the background, and this is what they did at Fermilat, and they also obtained a picture with only the acceleration sites, with only the so it will have, instead of a continuum, we will have spots. Now there is a large spot in the center because of the supermassive black hole, and so you can see also on the internet this version of the gamma rays sky with only spots instead of a continuous of gamma rays. Fermilat did a catalog of the various acceleration sites, and he measured the spectral index, which can be fit into an exponential. Oh, sorry, there's a minus sign here. Into an exponential, a decaying exponential, exactly like cosmic rays, which makes sense since these are gamma rays which come from acceleration of cosmic rays. And there is also a cutoff term which becomes important when we reach energies close to some critical energy EC. And the interesting thing is that it measured the index gamma ray alpha gamma for various acceleration sites, and the index for supernova remnants is of about 2.2, which is pretty close to gamma 0, which we have calculated with a Fermi acceleration mechanism of about 2 in the last video. and this makes sense because these are photons coming from acceleration of cosmic rays, so it is um, another evidence supporting the Fermi acceleration mechanism. And now we talk about gamma ray bursts, the most energetic events in the sky. We have seen um, the detection of gamma rays, and we have seen um, static static pictures of gamma rays. Because the sources of gamma rays we have considered last for a very long time. For instance, supernova remnants last for thousands of years, and instead gamma ray bursts are very brief events. They can last seconds or minutes, and they are very energetic and they saturate um, the gamma ray detectors looking at that spot in the sky. They were discovered by accident in the 60s. There had been the Treaty of Non-Proliferation on Nuclear Weapons, and America and the USSR were spying each other with satellites. They were looking for um, high energetic emissions or gamma rays to see if someone was testing nuclear weapons, and Americans detected um, very energetic gamma ray bursts coming from space. And this discovery was announced only a few years later, and since then we have been trying to um, build detectors in order to study these events. Important observations from 1991 to 2000 were done by Batzer, mentioned before. It had 8 scintillators because gamma ray bursts are quite rare events, and so if you do not want to miss them, you need to have a view of the whole sky. So it had 8 scintillators to map the whole sky, and but only 8 scintillators to map the whole sky. It means that every scintillator has a quite large error of detection, and so the detected direction is not very precise. But despite this, you could discover that gamma ray bursts are isotropic events. So they are either of extragalactic origin or of very nearby origin close to the solar system, because otherwise, if they were of galactic origin, they would um, they would be expected to be concentrated in the galactic disk. Batse could measure the duration of the gamma ray bursts. There are short gamma ray bursts and long gamma ray bursts, and the short are by convention considered those less than 2 seconds. Long gamma ray bursts are longer than 2 seconds, and it could measure the energy per square distance, not the overall energy because you would need to know the distance for that. But in fact, you could not measure neither the distance nor the energy separately. And to measure the distance, you would you could detect the gamma ray, the redshift in the afterglow of the gamma ray burst. But doing this, you need to tell optical telescope where to be pointed at in the sky, and so you need to know the precise direction of the gamma ray in the sky, which is something Batse with his 8 scintillators could not do. This problem would be solved only after other gamma ray burst detectors which were more precise and which, considering all the data from different detectors, could better locate gamma rays in the sky, gamma ray bursts in the sky, and so the first detection of the afterglow was in 1997, and by detecting the redshift in the afterglow, we could realize that they are indeed of extragalactic origin because they are very far away sources. So while you can detect a gamma ray burst in the sky, identifying its source is not straightforward. You need multi-messenger astronomy, and the first source which was identified, the first source of gamma ray bursts, was a source of long gamma ray bursts, and in 1998, which was a supernova. And short gamma ray bursts are much more rare and more difficult to identify. And the first time we identified a source of short gamma ray bursts was in 2017. In connection with the observation of gravitational waves from the same event. It was the uh, the, the, the merging of two neutron stars. High energy gamma rays, like from the order of the teraelectron volts, are pretty rare, and so to detect them, we do like high energetic cosmic rays. We do indirect detection from the ground. So this we have talked about this a bit in the second video, and we have talked about hadronic showers initiated by a proton or a cosmic ray, and showers initiated by a gamma ray. So the methods of detection are mainly the Cherenkov detector imaging, which basically takes a picture from the sky of the evolution of the shower from the light emitted by it through Cherenkov radiation, and it has a 10% duty cycle because you can do this only at night, at moonless nights. Instead, the extensive air shower method has a 100% duty cycles, but the results depend on the assumptions you made in the simulations used um, to reconstruct the to choose to reconstruct the initial gamma ray. And also with the extensive showers you can on the ground you can detect the types of particles, and in this case the um, the initiated by a gamma ray only has electrons and gamma rays. Instead, a shower initiated by a proton has also muons, neutrinos, as we have seen in the second video. This is all for today. See you next time.